Okay, hello. So what we're going to do, we're going to continue, give you the topics on the power series. Okay, we already defined a power series. We know the radius of convergent and the domain of the convergence or the interval. So now we are going to continue looking at the power series as a function so that we'll be able to differentiate it, integrating, and some very interesting applications, okay? So it would be 11.9. It's very dense and very important section. Let's go to my notebook. Okay, so this is going to be section 11.11.9. So this is going to be what we are going to do. So let's go back. This is called the representations of functions at the power series. You see, you have a function, you have a power series, you can change it to a function. And if a function is given to you, you can write it down as a power series, which is very important because the power series are like polynomials and very easy to handle. Okay, so this section, the title is representations. Okay, that's it. We give you a function and you want to represent it. So this is it. This is going to be a representations of functions. Okay, of functions as power series. Power series. Okay, that's what's the one. So what's the idea? Suppose you have a power series. You see, suppose a power series is given to you. Okay, so suppose the power series, the general one, the power series, okay, sigma of Cn times x minus, let's say x minus a to the n from 0 to infinity. That's a general power series. Suppose it's given to you and you have the radius of convergence, has a radius, okay, has a radius of convergence, R. And we assume that, of course, R is not equal to 0. 2, 3, 4, 5, 6. You see, if this is going to be the case, this means if you pick any x whose absolute value of x is less than R, then if you substitute the x, this series would be convergent. When it's going to be convergent, so you get the limit. So we can find the sum of the series. So anytime you pick an x, okay, see this is what we're going to do. You see, if you pick the x, pick the x, this condition of the x, that x is going to be absolute value of x is going to be less than R. So this means x is in the domain of the convergence. Okay, then if you drop this one into the f function, then you want to find f of x. So f of x would be defined by the limit of this series, sigma of Cn x minus a to the n from 0 to infinity. You see, because anytime you get the x, you see you drop it into the series is convergent, and the sum of the series would be a number. Then you pick another x, as long as it's going to be in this domain, the series is convergent. So the numbers that you're going to get as the limit, as the sum of the series would give you your function. Okay, so this is going to be f of x equal to the Cn times x minus a to the n. This is going to be true when x is going to be what? And x is going to be between, okay, just the domain of the convergence, okay? So this is going to be the case where that's not correct. Just, because the series going from x minus a. So the x minus, I write it down here. So this is going to be when when the absolute value of x minus a is going to be less than r, or when x is going to be between, okay, x is going to be between a plus r and the a minus r. Okay, so this is just the interval of convergence. So in this way, we are going to have a function. So f is going to be a function. F is going to be, f is defined by a power series. So f is defined by a power series. Okay, a power series, and is going to be called, f is called a function represented by a power series, See, previously you have polynomials, a function that's represented by a polynomial. Okay, so you have a radical function, a function represented by a radical, sine function, cosine function. So this is a power series function. So as long as the domain of this function, you see the domain of the function, the domain of the function f is going to be, is the same as the interval of convergence. Okay, convergence of the power series. Power series. Okay, so this is going to be a function represented by a power series. Now there are a couple of famous ones, and we can use that from now on up to the end of the course. This is going to be your job. You see, the job is going to be, if a power series is given to you, so it's going to be convergent for the x's in the interval of convergence, you create the function f. So on the other hand, if a function would be given to you, you should be able to write it down as a power series. So this is going to be your job, writing the power series representation for a function. So to do it, this example is very crucial. We are going to have various theorems that we are going to study, but practically when you want to use it, you are going to use this example. Okay, so this is going to be the key example. So what's going to be this example? Consider this power series. Consider the power series. Let's see if you can recognize this one. You see this power series, sigma of x to the n from 0 to infinity. You know that if you replace n by 0, so the first term is 1. Replace n by 1, we get x. We get x squared. Okay, continue x to the n forever. Look at this one. So if you think about it, this is like, we have the first term, which is 1, and we multiply everything else by x. So as you can see, this is the geometric series. It's a geometric series. The common ratio is x, and the first term is 1. So this is going to be a geometric series. Okay, geometric series is going to be geometric series with the first term. Remember, a is equal to 1, and the common ratio r equal to the x. Okay, and so you know that a geometric series is convergent if the absolute value of r is less than 1. So therefore the series converges. You know that converges when the absolute value of r is going to be less than 1, or because the r is x. So, or when absolute value of x is going to be what? Absolute value is going to be less than 1. When the absolute value is less than 1, you know that this is convergent, and the sum of the series and the sum of the series, you know that it's geometric, so the sum is what? The sum, remember, S was A or A1, the first term, over 1 minus R. So A is equal to the 1, R is equal to the X. So let's give you this one. But this is going to be the sum of the series of the power series. So what do we have? We have the fact that, okay, you are going to have this one, that sigma of 1 over x, so the sigma of x to the n from 0 to infinity is going to be equal to the 1 over 1 minus x with one condition. The condition is that when absolute value of x is going to be less than 1. So as you can see, this power series can be represented by this function. The function is 1 over 1 minus x. So you have a power series representation of the function. Okay, so let's give you to go to the next page and continue. So basically this means, okay, so what we did, therefore the function, you see the function f of x equal to the 1 over 1 minus x is represented. It's going to be represented by a power series. Power series. That's it. You have 1 over 1 minus x. Okay, so this is going to be sigma x to the n in expanded form, is in shrink form. And this would be what? This would be 1 plus x squared forever. But one condition, absolute value of x must be less than 1. If you drop this condition, you are out, because this series is convergent, and it's going to be equal to the 1 over 1 minus x. Only you know that if the common ratio is less than 1. So we arrive at this famous formula that you can memorize it, and you can use it anytime you like in this course. So 1 over 1 minus x is equal to the 1 plus x. You know, expanded sometimes would be better to memorize it. Okay, this is the case, but make sure that you write the condition. Absolute value of x is less than 1. Okay, you can use this one anytime you like. So on one hand, it's a function, 1 over 1 minus x. On the other hand, is represented by a power series. So it is a power series functions, if you like. Okay, and you can change this one and get various formula if you like. Let's call this one a star equation. So you are free to use this one anytime you like. But you can get more. You see, look at this one. So I'm going to give you various conclusion of this that you can use it. You see the first one. If you replace this x by negative x, so this is it. Replace x by negative x. By negative x in this star equation. That give you another one that you can use it anytime you like. You see, that would be what? Replace x by negative x, that give you 1 over 1 plus x. So the first term would be 1, but the second one is a negative x. Then this is it, negative x squared, that give you positive x. But the next one is going to be negative x cubed. And then you get a positive x to the 4. So the general term would be negative 1. Okay, negative 1 to the n, x to the n, forever. What's the condition? The condition that absolute value of negative x to be less than 1. But the absolute value of a negative x and the absolute value of x is the same. So you are going to have 1 over 1 plus x is equal to the expanded in the dense form, if you like, -1 to the n, x to the n from 0 to infinity, or just 1 minus x plus x squared minus x cubed, etc. With the condition that the absolute value of x is less than 1 again. If you don't bond this condition, you can't do it, remember, because your series must be convergent. So again, you can use this one anytime you like. That 1 over 1 minus x, and you can create more to get this information, okay? So function 1 over 1 plus x can be represented by this series, -1 to the n, x to the n. The function 1 over 1 minus x can be represented by only sigma of x to the n. You can have another one that we use it from time to time. If you replace this x by x squared, okay, if you replace x by x squared, so what are you going to have? You have a new function. You see, you can make more and more and more function. So that give you 1 plus 1x squared equal to the sigma of -1 to the n. Replace this x by x squared. So that give you x squared, raise it to the n. Okay. So this is, you have a old power and the new power. So it's going to be sigma of -1 to the n, x to the 2n. Okay, we multiply this together, and the condition would be the same. You see, the condition is the absolute value of x squared less than 1. That gives you absolute value of x less than 1. So you have a formula for this. You see, 1 over 1 plus x squared is equal to, again, like changing these, is going to be 1 minus x squared. 1 minus x squared plus, okay, 1 minus x squared plus x to the 4th minus x to the 6th, etc. when the absolute value of x is less than 1. So you should be prepared to get these power series representation of various functions. All these three that I write over here are going to be used in a minute to get a power series representation of more function. But the point is, anytime you use this one, you see the radius of convergence is going to be 1. You see, absolute value of x less than 1, less than 1, less than 1. If you don't write it, you are not going to have it, okay? So we can use these three to find more functions. Power series is a representation of more functions. So this is going to be your job, that you are going to be asked to find the power series for a given function. Okay, so get the advantage of this. We are going to have more methods, but this is a very quick one. And with this one, you'll be safe forever. You can have very difficult problem really and just take care of it. Look at this one. The possibilities. We give you a group of them in your next quiz and of course on the final. We give you a function and we would like you to write it as a power series. So we'd like you to find, okay, we'd like you to find a power series. Find a power series. Power series representation for each function, or each of the following function. There are a couple of tricks that I'll show you, then you'll be fine. Following functions, each of the following function. Okay, that's it, function or functions. Okay, let's take the first one. You see the first one, it's f of x equal to 1 over. You see that's it, it's going to be 1 over 1 plus 2x. That's it. You have to connect it to the geometric series that I talked about. It's the only way to do it, because this is 1 plus. So what are we going to do? So that's the first one. You see, look at this one, solution. Let's start with the one that you have for the geometric series. This geometric series, 1 over 1 minus, look, another x like this one. So that was equal to what? it's equal to the, the sigma form is, that was equal to the sigma of x to the n from 0 to infinity. Geometric set is 1 plus x squared, etc. with the condition that the absolute value of x is less than 1. You see what you want? 1 plus 2x. So replace the x by negative 2x. Okay, so you're going to let x to be negative 2x. Substitute. If you substitute here, that would be 1 over 1, negative, positive, so that give you 2x. Equal to, that's a sigma of, replace the x by negative 2x to the n from 0 to infinity. You see? So that would be your expanded form, if you like. You can continue to get this expanded form, or just go for it to get the numbers. Okay, so if you like, this is going to be a kind of, you can put it out. This is going to be negative 2 to the n. Okay, if you know, you can substitute here and then find out what is going to be the result, or just simplify it. So this would be equal to the sigma of, that would be negative 2 to the n and x to the n from 0 to infinity. Okay, and but the condition that we have, you see the condition is absolute value of a 2x, or the negative 2x, absolute value of negative 2x to be less than 1. So if you expand this one, n equal to the 0, you see that give you 1 over 1 plus 2x. If we replace n by 0, that give you 1. Replace by 1 like the original one that you have. You see, you should replace this one by negative 2x. Then the next one would be a positive. So that's going to be positive 4x squared. You square it. And the next one, you see 2 to the third would be 8. You get 8x cubed, and then you continue. Now the absolute value, you can pull out the negative 2, so that gives you 2 times the absolute value of x is less than 1. Okay. Then this you solve for the absolute value. So your series would be 1 over 1 plus 2x, 1 minus 2x plus 4x squared, okay, minus x cubed. If you want to write the general term, you can do it. It's going to be, your general term is negative 2 to the n, okay? So that is going to be negative 2 to the n, x to the n. But what is the condition? Absolute value of x to be less than, you see, divide by 2, less than half. So this would be a power series representation for your, okay, for your function. Okay, so basically you start with the one that you have, geometric series. Quickly replace the x by negative 2x. X by negative 2x, but you have to replace everything. Absolute value of x with the absolute value of 2x. So you have to solve for x, that gives you absolute value of x less than 1/2. Then you can expand this one in the expanded form or just sigma form. All of them would be acceptable, and we are going to use it. Okay. So that's first one. It's not x is a 2x, so just replace it. You get the result. That's one case. What's going to be the next one? The next possibility is they give you this function, f of x equal to 1 over x plus 3. You see, if you compare it with the geometric series, you can do it only if it's going to be 1 plus x, but this is 3 plus x. So what you can do, you can factor out the 3. You see, look at this one. So the solution would be, you have 1 over, okay, 1 over x plus 3 factor out the 3. So that give you 3 out. So this x would be x third, and that would be 1. Okay, pull out the third. That give you 1/3, 1 over 1 plus 1 plus x third. You see that's 1. But remember, so you note that. Go back to that series that you have. So what we have, geometric series, 1 over 1 minus x is equal to what? Is equal to the 1 plus x squared forever, with the condition that the absolute value of x is less than 1. Now replace the x by negative x third. So that's x, negative x third. So that gives me 1 over 1 plus x third equal to, replace all the x by x third. So that would be 1 plus x third. Okay, 1 plus x third. This would be x third squared. Okay, and you just continue. The last one would be x third. Okay, this is it. This is going to be x third to what? We just replace it by a negative x third. So this is going to be, okay, that gives you a plus. So over here, this is going to be negative positive, sorry. So negative, this would be positive. So if you continue, the general term is going to be something like negative 1 to the n, x third to the n. The condition is going to be the absolute value of x third less than 1. Okay. So if you want to break it a little bit more, this is what you are going to have. Remember the original one, you have a 1/3 times. So this is what you are going to do to get the final answer. So originally I rewrite it is x plus 3. We factor out the 1/3. Remember, it's going to be 1/3. And that was 1 over 1 plus x third. So this is going to be equal to the 1/3. Now the series that you bring for this one. What was the series? 1 minus x third plus you square it, x squared 9, minus you cube it, x to the third, okay, 27. 27, and you continue. You see, you continue. So your general term, if you like, is going to be something like a negative 1 to the n. Okay, x to the n. You see, this is first power 3 to the first, x squared 3 to the second, third. So it's going to be x to the n over 3 to the n. What is the condition? The condition is that the absolute value of x third to be less than 1. So you can multiply a third inside. So this is going to be 1 over x plus 3 equal to the 1/3 minus x, that give you 3 squared. You move the powers. That give you x squared. If you like it, this is going to be 3 to the third. Okay, that would be 3 to the fourth, etc. So the general term would be negative 1 to the n, x to the n, 3 to the, you see 1 up. You see 1, 2, 2, 3, 3, 4. So that gives you 3 to the n plus 1. What is the condition? You see, you pull out this, it's going to be absolute value of x divided by 3 less than 1. And that give you multiply by 3, so that gives you the result. So this is the power series representation of the given function. It's going to be 1/3 minus x over 3 squared plus x squared over 3 to the third, etc., with the condition that the absolute value of x is going to be less than 3. Okay, I write it down in expanded form, but you can do it in the brief form. with the sigma notation. I tried for you. You see, if you like method 2, it's just a notation would be different, but it is going to be the same thing. See, look at this one. I repeat it again. The first part, the factoring, it must be done. You see, it's 1 over x plus 3. You factor out the 3, so this must be 1 plus. So it's going to be 1 over 1 plus x third. So you see what I'm going to do? Look at this one that I gave you. 1 over 1 plus x is alternatively positive, negative, positive, negative. So this is the general term, negative 1 to the n, x to the n. So what I'm going to do, I'm going to check this. This is going to be 1/3. And this is going to be what? This is going to be sigma of alternatively positive, negative, positive, negative. So that gives you negative 1 to the n. X is x third. X third to the n from 0 to infinity, with the condition that the absolute value of x third to be less than 1. So that's quick one. So you simplify it a little bit. This is going to be 1/3 sigma of negative 1 to the n. It's a fraction. You raise the top and the bottom. So the top would be x to the n. The bottom one would be 3 to the n. And you solve this one for the absolute value of x. You multiply both sides by 3. So absolute value of x is less than 3. N from 0 to infinity. You see, but this is 1/3. You multiply inside. 3 times 3 to the n would be 3 to the n plus 1. So it's going to be sigma of negative 1 to the n. The top would be x to the n. The bottom one would 3 to the n plus 1. Okay, n from 0 to infinity. And the condition that the absolute value of x is less than 3. You see, this is your function. That's it. So you're going to stay with the sigma. It's easier for this type of problems. Now, if you want to write a couple of terms, you see, you replace n by 0. N by 0, that give you, the top is going to be 1. That give you 1/3. You see, this is the 1. Even if you want to expand it. N equal to the 0, the first term would be 1/3. Replace n by 1. It's going to, alternatively, it's going to be positive, negative, positive, negative. So it's going to be 1. N by 1, the top would be x. N by 1, the bottom one would be 3 squared. Then you continue. That gives you x squared if you replace n by 2. So that gives you 3 cubed. Minus x to the third, 3 to the fourth, etc. But absolute value of x less than 3. See, that gives you the result, by the way. Great method. You are going to learn another method later on. But this is a very good one. So you need only, you see, you need only these two. 1 over 1 minus x geometric series. 1x x squared or sigma x to the n. With the condition that the absolute value of x is less than 1. If it's going to be 1 plus, it's alternatively. So these two would solve all the problem for you in this course, really. Just get to know it. Get to know it quickly to be able to do it. Okay. So let's make it more complicated if you like. See the one that I gave you this one, x plus 3. You factor out the 3 to make it to the 1 plus. So that was 1. The other one that I gave you was what? The other one, was 1, but we get the 2x. So we replace everything by 2x. If you want to make it more complicated, is the next one. See, look at this one. So that was number 1, 2. Let's have a number 3. Or maybe kind of 5 when we finish it. Number 3. How about this one? You want to find a power series representation for this function. Look at this function. F of x equal to the 1 over 2x plus 3. See? Again, you have to get rid of these 3. Because we can do it if it's going to be 1 plus. Okay, so it's easy. Just factor out the 3 solution. So this is 1 over 2x plus 3. It's going to be equal to, factor out the 3, 1/3, 1. So you divide this one by 3, that gives you 2x third plus 1. If you rewrite it to get the, but what's the condition? Or nothing, no condition at the moment. So this would be 1/3, and this is like 1 over 1 plus 2x third. Now we can get to the power series, 1 over 1 plus x. Alternatively, positive, negative, positive, negative. So it's going to be 1/3. This would be sigma of, since it's a positive, negative 1 to the n from 0 to infinity. Whatever you have, 2x third to the n. 2x third to the n, with the condition that absolute value of 2x third is less than 1. Okay, so what I did, I just used this identity. 1 over 1 plus x is alternatively positive, negative, positive, negative, negative 1 to the n x n. That's exactly what it is here. You see? So I just replaced 2x by third to the n, but the condition is this one. Now you have to solve for x. You see, this is 2/3 of the absolute value of x is less than 1. You divide by 2/3. So that gives you absolute value of x less than 3/2. So your power series is this one. 1 over 2x plus 3 is going to be equal to 1/3 sigma of negative 1 to the n, the top to the n, the bottom to the n, so 2 to the n, x to the n over 3 to the n, and from 0 to infinity, with the condition that the absolute value of x is less than 3/2. That's it. That would be fine, but you can move the 3 inside if you like. So if you move the 3 to times 3 to the n would be 3 to the n plus 1. So finally, 2x plus 3 is going to be equal to the sigma of n from 0 to infinity, negative 1 to the n. You see, that is going to be 2 to the n, 3 to the n plus 1, because 3 times 3 to the n, xn, with the condition that the absolute value of x is less than 3/2. That's a power series. If you want to write a couple of terms, you see, replace n by 0. That gives you 1, 3, 1/3. That's the first step. If you replace n by 1, that gives you minus by 1, 2, 3 squared x. That's the second term. If you want to continue, n by 2 plus 2 squared, 3 to the third, x to the, okay, x squared. And then you can get, can negative, positive, negative, positive. You get all of them. Okay, so it's possible to write all those type of power series using this one, which is very, very popular to get these numbers. Okay, get to know it. This is your tool. You're going to have a number of more theorems, but at the end of the day, we come back to this only. Give another one. Suppose you want to find the power series for this one. F of x equal to something like x squared on the top. X squared on the top, but x plus half here, okay, x plus 2 here. Remember, this is absolute value of x is less than 3. Because you can do it only if you have this condition. Now look at this one. You need a power series. You see, x squared is just powers of x. So what you do is you are going to ignore the x squared. You are going to find the power series for 1 over x plus 2 first. Then you multiply by x squared. Because you have only powers of the x, if you multiply by x squared, the leftover is going to be powers of x again. So you're not going to lose anything, okay? So the idea for this is going to be, once more, do 1 over x plus 2 first. 1 over x plus 2. You have to make this one into the 1/2 out, or 2 out. 1 x half plus 1. Rewrite it 1/2, 1 plus x half. Now expand this one. It would be alternating geometric series. So it's going to be equal to the 1/2. Okay, sigma of, since it's a positive, it's going to be -1 to the n, x half to the n from 0 to infinity, condition, absolute value of x half must be less than 1. Okay, it's a geometric series, but the common ratio is x half rather than the x. Simplify it a little bit, x to the n, 2 to the n. It's going to be 1/2 sigma of -1 to the n, the top x to the n, 2 to the n from 0 to infinity. Solve for x, you see multiply both sides by 2, so the absolute value of x less than 2. Okay, 2 inside, so that gives you sigma of -1 to the n, x to the n, 2 to the n times 2 will be 2 to the n plus 1. N from 0 to infinity, when the absolute value of x is less than 2. You see, that's a power series. But you have x squared divided by x plus 2. So what you're going to do is, you multiply both sides. You see that so far, this is 1 over x plus 2. Multiply both sides by x squared. So if you times it by x squared, so that will be the one that you are interested in. And this is going to be equal to, you multiply the inside by x squared. You take it in, -1 to the n. You have x to the n, 2 to the n plus 1. Now times it by x squared, with the condition that the absolute value of x less than 2. Now x to the n, x squared, you see you have the common base, which is x, you add the powers together, n plus 2. So your final answer is going to be, you see I'm going to add this, I change the x to the n into the x to the n plus 2. So the final answer, you have a nice, there are other methods. If you want to do it, then do quite a lot, but this method is such a nice one. Okay, so this is the final answer. X squared over x plus 2 is going to be equal to, okay, it's equal to the sigma of -1 to the n, x to the n plus 2. Remember that was x to the n and the x squared. So look at this one. So this is what you have. You see, this is x to the n, x squared. So the base x, you add n and 2, n plus 2. Okay, n plus 2, and divided by 2 to the n plus 1. N from 0 to infinity, condition, absolute value of x less than 2, and you're done. If you want to expand it, if you replace n by 0, so you start with the x squared. You see, it's going to be n by 0, so the top would be x squared. The bottom one would be 2. So that's your first term. If you replace n by 1, that would be minus x to the 1 and 2 would be 3. 1 and 2 would be 2 squared. If you write a couple of terms, you'll get the general term. Okay, if you replace n by 2, so that gives you x to the 4. So that gives you 2 plus 1, 3. See? 4, 3, 3, 2. This is positive, the next one would be negative. You see x to the 5th, 3 to the 4th. And you continue with the condition that the absolute value of x is less than 2. So that's a power series representation for the given function. Okay, so nicely connect everything to that geometric series. That's a key. Okay. Now what else? In order to be able to have more power series, we are going to define how we're going to differentiate or integrate power series. You see, we talk about power series as a function. Since the function, it can be differentiated or we can integrate it. So we're going to differentiate this series. So what we're going to do, we differentiate each term, you see. We differentiate the first term, the second term, that. How we're going to integrate it? We take the integral inside. So let's talk about it. That will help you to be able to write. You see, so far you can only write the one that is very close to the geometric series, but we have lots of functions. So I'm going to write the power series for those functions. So this is what we want. So differentiating or differentiation, we're going to find the derivative. Okay, that's it. So differentiation and integration of power series of power series. You see, if you want to differentiate, find the derivative of the power series, you just find the derivative of each term if you like. If you want to integrate it, just find the integral of each term. So this is what you are going to have for the power series. Okay, so officially this is it. Suppose again you have a function f of x is equal to the sigma of general one Cn x minus a to the n from 0 to infinity. Okay, this is going to be the function. And with the common receiving, as usual, absolute value of x minus a is less than r. We need the domain of the function. The domain of the function is going to be the domain of the convergence. Okay, if this is going to be the case, then you see all the properties that we know it. The first one, f is continuous. F is continuous on the domain of the convergence. You see, on interval of convergence. You know that if you take out this one, it's going to be x between a plus r, and you see domain of the convergence is going to be a minus r and a plus r, or when the absolute value of x minus a is less than r. So the power series are continuous function. Second one, it's differentiable. So f is differentiable. Okay, it's going to be differentiable again on this domain. This is the same as the interval of convergence. And what's the derivative? F prime of x. You go inside and differentiate this one. Cn is a constant. It's like x to the n. So that gives you sigma of Cn. Derivative, you bring the n down, times n, x minus a to the n minus 1. But n must start from 1 to infinity, not 0. Because if you put the 0, the power will be -1, and you know that. You cannot have the negative power for the power series. Okay, so this means if you want to differentiate the power series, differentiate it term by term, as we do it for the polynomial. The next one is integrable. You can find the integral. F is integrable. And how we're going to find the integral of the power series? You see integral of the f of x dx. You go inside and integrate. Cn is a constant. If you want to find the integral of this, you know that the power series. Integral of the power rule, x minus a to the n plus 1 over n plus 1. So it would be sigma of Cn x minus a to the n plus 1 over n plus 1, n from 0 to infinity. Okay, so this means you can differentiate term by term, or you can integrate it term by term. The radius of convergence would stay the same, but the interval of convergence may be different. Okay, let's see how we're going to use it to get those numbers. Okay, now give you that remark that we did have before that would be helpful. You see, for example, we got this one. So recall that we know this. You see, recall that. Remember that the geometric series 1 over 1 minus x is equal to what? Is equal to the 1 plus x squared, etc. Okay, the general term is x to the n, and the condition is the absolute value of x is less than 1. Now differentiate both sides. What's going to be the derivative? Differentiate both sides. You see, the derivative of this one is quotient rule, derivative of the top times bottom. Derivative of the top, derivative of 1 is 0. Times bottom would be 0. Derivative of the bottom times top. Minus derivative of the top there, bottom there. But derivative of the bottom is negative 1. You have negative, make it to the positive. So that gives you derivative of this part's going to be 1 over 1 minus x squared. On the other side, derivative of 1 is 0. Derivative of x is 1. Okay, so we start with the 1 plus derivative of x squared is going to be 2x. The next one would be 3x squared, etc. And derivative of x to the n would be nx to the n minus 1. Condition would be unchanged. So in general, if you want to have the expanded form, 1 over 1 minus x squared is equal to the sigma of, you see the derivative of x to the n x to the n minus 1, n from 1 to infinity, not 0. Because this is n minus 1. If you put n equal to 0, that equals x to the negative 1. And the condition is the same. Such an important formula, you see. Nicely, you can use it. So if you want to write the power series representation of something that there's no power on the denominator, you use this one. But if you want to have the square, differentiate it. If you differentiate it again, that gives you to the power 3. If you differentiate it again, that gives you to the power 4. So it depends what you want. If you want various powers, you can make it over here. Okay, so again, we are going to use it in order to get the power series representation of the functions. And there are a couple of them, which is very famous, and you must know it. Okay, so let's get back our job. The function would be given. Would like to get the power series, okay, a representation of the function. So you can, if you want to differentiate term by term. If you want to integrate term by term. Let's see how we're going to use it. Okay, very famous problem is this one. So, example. Example is going to be, we want to get the power series representation again. Write a power series representation of each function. are two very famous ones. You have to know it. That's it. The first one, the most popular one. You see f of x equal to the ln of 1 plus x. It was done by Euler for the first time. Okay. You see, it's not a geometric series, so you can't do anything about it. So what we're going to do now, you see, you differentiate it. If you differentiate it, what's the derivative of the ln of 1 plus x? You see, this is ln u. Derivative would be u prime u. U prime, derivative of 1 plus x is 1, u 1 over 1 plus x. You see, look at this one. For the solution, you note that you see derivative of this function is u prime u. U prime, derivative of 1 plus x, 1, u. You see? So the derivative is the familiar function. This is 1 plus 1 over x, and you know that you can write a geometric power series representation for this one. So what's going to be the power series representation? You see, this is going to be equal to the, if you like, it's a sigma of -1 to the n, x to the n, and from 0 to infinity. Okay, which is 1 minus x plus x squared, etc. With the condition that the absolute value of x is less than 1. So when we differentiate the function, we can get the power series representation. So in order to get back to the function, integrate these two parts. If you integrate both parts, you should look at this one. So this time, take the integral of both sides. The integral integral of both sides. You see, you integrate this one, it's going to be 1 over 1 plus x dx. And you integrate the other side. It's going to be integral of the power series. You know that the integral of the power series, you take it inside. You see, that's what? Integral of sigma of -1 to the n, x to the n. And from 0 to infinity. You see, you can add the constant c, or you can integrate, let's say, from 0 to x. Because you don't have to have a constant c. Now, integral of 1 over 1 plus x, you know that gives you ln of 1 plus x. How about this one? We take the ln inside, integral inside. So that gives a sigma of -1 to the n, integral of x to the n dx. And from 0 to infinity. But integral of x to the n, you know that that's just the okay, just the power rule that gives x to the n plus 1. So that gives a sigma of -1 to the n from 0 to infinity, and that would be what? X to the n plus 1 over n plus 1. With the same condition, the absolute value of x is less than 1. See, you create a nice formula. So this is it. We prove that the ln of 1 plus x is equal to, that's the power series form, sigma form. You can expand it if you like. If you replace n by 0, and that gives you x on the top. Replace x by 1, that gives you a negative sign. So that gives x squared. You see x squared. Replace n by 1, 1 and 1 would be, okay, would be 2. If we replace, that was 0, 1, if we replace it by 2, so that gives a positive. Replace it by 2, 2 plus 1, 3. 3, and the 2 plus 1 is 3, you see? And then you can guess what's going to be the next one. X to the 4th over 4, x to the 5 over 5, etc. But the condition, absolute value of x is less than 1. This is a power series representation for the ln of 1 plus x. Very nice one. You get these numbers. You see, that's going to be 1. Euler did this one, and what he did is he just replaced the x by 1 on both sides. So if we replace this by 1, 1 and 1 would be 2. So you get ln 2. And over here, you get 1 minus 1/2, 1/3, okay, a quarter, etc. And you know this series. Remember harmonic alternative series. So you get ln 2 here, and here is a sigma of -1 to the n. Okay, remember? -1 to the n over n. N from 0 to infinity. So remember this series? We worked with this series before, and always we say it's convergent, because that was alternating, okay, alternating harmonic series. Remember the Bn was 1 over n, limit of the Bn is 0. But we never talk about the sum of the series because we didn't know it. Now we can do it, you see. This is the first time the Euler did this one. Use this power series representation of ln of 1 plus x to be able to find the ln of 2. And we are going to do a couple of these things. Okay. So that would one advantage of differentiating and integrating in this case. Okay. So this is the way you think about it. There are some other methods, complicated methods, to be able to do the same thing. But these are the trick, very easy. So try to connect everything to the geometric series. Make things easy for yourself. Of course, it's not the case that we can do all of them, but most of them can be done. So for this one, we just differentiate it. We find out that derivative can be represented by a geometric series. See 1 over 1 plus x. Then we integrate it to go back. Integration, you do it term by term, you just integrate x to the n. Differentiation, you do only x to the n to take you back, okay? There is another very famous one that you have to know it in this course. This is one of them. We may question you on the test or the quiz 4 and the final. And another popular one is this one. Okay, number 2, you must know this one too. The function is that famous function, tan inverse. Tan inverse of x. We want to write the power series representation for this one. Of course, it's not geometric series that we be able to do it. Okay, it's not. Check the derivative. Remember the derivative of tan inverse is 1 over 1 plus x squared. It's geometric series. Done. So we get this one. Differentiate it. Derivative is 1 over 1 plus x squared. That's it. Remember, you can use the alternating series of the geometric series, but replace x by x squared. And I did it before. So this would be what? This is equal to geometric series, alternating one, sigma of -1 to the n. Remember, x squared to the n, or x squared to the n from 0 to infinity. It's going to be x to the 2n. So it's equal to the sigma of -1 to the n, x to the 2n, n from 0 to infinity. You see, that is 1 over 1 plus x squared. Of course, the absolute value of x is less than 1. Again, geometric series. I just changed the x into the x squared. I use the alternating one because this is positive. Now, again, integrate. If you integrate both sides, so that you 1 over 1 plus x squared dx, and integrate this one, you know that you go inside -1 to the n, you integrate in x to the 2n. This integral, you know that it's going to be tan inverse. But for this one, you integrate x to the n. So it's going to be sigma of -1 to the n. Now x to the 2n plus 1 over 2n plus 1. Of course, make sure you know the condition. Absolute value of x is less than 1. and n from 0 to infinity. That's it. You see, great series. What is the series representation for tan inverse? Replace n by 0, so that give you x. Replace n by 1, that give you minus x. Replace n by 1, 2 and 1, 3. 2 and 1, 3. Replace x by 2, so that give you plus x to the 2, 2, 4, 5, 5. So you get only odd power. So the next one would be negative x7, 7. And you continue with the condition that absolute value of x is less than 1. You see, nice. You get a nice representation of the okay, of the tan inverse of x. So that show you the tools, okay, that we have, something very strong that we have to we can take care of these type of functions. Okay, so this is 11.9. So what we did, we show that the power series are differentiable, power series are integrable, and we help you to write down how we're going to write the power series of various functions. But the key is that geometric one. Okay, so what we're going to do next thing, that would be enough. So I want to give you time to think about it. The one that we did. Then what else we can do so that you know the power series. There is another method to be able to create the power series for other functions. That method is going to be Taylor series. So we have to discuss that. It's a long argument, but at the end of the day, there is a theorem that will tell you that this Taylor series exists. But when you want to do it, you have to get back here. But we have to define the Taylor series for you, okay? So think about this and check the 11.9. There are some very nice problems. And I will post a couple of worksheets for you from now on. And I give you extra points if you do it, because we need this type of worksheet, okay? So I posted and put a deadline for you. After that, I will give you the solutions because we need it before the final. Okay, so that's so far. It's very important, this method that I did. Just think about it and I post that worksheet, just try it. So, because all the problem in the final would be related to this one. Taylor series seems to be complicated, but it's not. I slowly talk about it next week. Okay, that's it. Have a good one and get practice and look at the worksheet that I'm going to post for you. Okay, bye-bye.